is one solution because 3 squared plus 4 squared is equal to 5 squared. In fact, we can multiply these solutions by any number. Let's say, let's multiply this by 5, or let's multiply it by k. Okay, let's multiply this by k. If we multiply it by k squared. If we multiply by k squared, we get 3 squared k squared plus 4 squared k squared is equal to 5 squared k squared. So we get 3k squared. Quantity 3k squared. We have quantity 4k squared. And we have quantity 5k squared. This means that if we have one Pythagorean triple or a solution, by multiplying that solution by any integer, we get another Pythagorean triple. So it means that whatever our k is, 3k plus 4k is 5 and 5k constitute another solution. Right? So another solution, other solutions are well, let's look at this first. Let's multiply by 2 or by 3. So if we multiply by 2, we get 6, 8 and 10.
9, 12, 9, 16.
If we multiply by 3, we get 9, 12, 15. If we multiply by 5, we have 15, 20, 25. In fact, we'll never run out of solutions. Just like for linear Diophantine equations, similar to linear Diophantine equations where one solution would give us so many solutions, here we have a single solution giving us infinitely many solutions because we can multiply it by any number. We call solutions to a Pythagorean equation a Pythagorean triple. So a solution to a Pythagorean equation is called a Pythagorean triple. A triple is just a set of integers. So, for example, 3, 4, 5 is a Pythagorean triple. 6, 8, 10 is a Pythagorean triple. 9, 12, 15 is another Pythagorean triple. Except that, you find this interesting. Well, all of them come from 3, 4, 5. Yeah. So in this set of solutions, we can think of 3, 4, 5 as the mother solution or the father solution or the original solution. This is actually more interesting because look at this. If you look at these three numbers, they have a common divisor 2. This is common divisor 3. This is common divisor 4. However, this has common divisor 1. No? We have a special name for this. We call this primitive Pythagorean triple. A primitive Pythagorean triple is a Pythagorean triple whose GCD is 1. In our examples, 3, 4, 5 is a primitive Pythagorean triple. 6, 8, 10 is not a primitive Pythagorean triple, but it comes from a primitive Pythagorean triples. Yeah. So every time you have a Pythagorean triple, you just cancel out the common factors, and you will get a primitive Pythagorean triple. So in the case of 5, 20, 25, the common factor is 5. So you just divide everything by 5, you get a primitive Pythagorean triple. So what we are really interested in are looking for the primitive Pythagorean triples because all triples will come from the primitive Pythagorean triples. Now, the Greeks actually had Now, let us think of other Pythagorean triples that we know, aside from 3, 4, 5.
12, 13.
We have 5, 12, 13,
5, 23,
5,
23, 24,
do you know this?
25.
Or this? These are all called primitive Pythagorean triples. But in fact, the Greeks knew that there was a way of getting all primitive Pythagorean triples. And perhaps even the Babylonians knew this. Because if you remember during my first lecture, we saw pictures of ancient civilizations having very large tables of Pythagorean triples. So somehow they had a method of computing those Pythagorean triples. And this is the method known to the Greeks. Every primitive Pythagorean triple, ABC, where A is odd and B is even, can be obtained using these formulas. A is equal to m squared minus n squared. B is 2 times mn. And C is equal to m squared plus n squared. Here where m and n are positive integers, such that m is greater than n, and the GCD of m and n is 1. This means that we can choose any two integers, m and n, that satisfy this. And we have a solution to the Pythagorean theorem, Pythagorean equation. Well, here it says that A and B are odd and negative. So you can see that A and B here are always different in parity. It means one is odd, one is even. Of course, they cannot be both even, right? Because we want them to be primitive. If they are primitive, then they should share, they cannot share a common factor. And it is not difficult to show that they cannot be both odd. In fact, one has to be even, one has to be odd. And this is what we have. In fact, we can, x, y, and z, m, and n. Oops, I used A, sorry. A, B, is C. Suppose we want to list down Pythagorean triples A, B, C. And we want to identify the numbers m and n that would give us the Pythagorean triples A, B, C. For example, if A is, we know that 3, 4, 5 is Pythagorean triple. Can you identify the values of m and n that would give you 3, 4, 5?
2 and 1.
2 and 1. A is equal to m squared minus n squared. So that 2 squared minus 1 squared is 3. B is equal to 2mn. So 2 times 1 is 4. C is equal to m squared plus n squared. So that's 2 squared plus 1 squared is equal to 5. How about 5, 12, 13? You can actually look at B. Remember, B is equal to 2 times mn. So you divide B by 2, you get 6. And try to think of those two factors that would give you 6. Okay? 7, 24, and 25. What is this? 4 and 3. So B is 2 times mn. So mn must be equal to 12. And the two numbers that would give you that are 4 and 3. And you can check. 4 squared minus 3 squared is 7, right? 4 squared plus 3 squared is 16 plus 9, and that's 25. No? How about 9? 40 and 41.
5 and 4. 5 and 4.
5 and 4. In fact, we can choose any pairs of numbers 7 and 3, m and n. If we choose 7 and 3 as our m and n, what are the values of a, b, and c? We can check. 7 squared is 49 plus 3 squared, which is 9. That's 49 plus 9 is 58. So this must be 49 minus 9 is 40. 2 times 7 times 3 is 42. 49 plus 9 is 58. No, this is not a primitive Pythagorean triple, but it is a Pythagorean triple. No? So if we want our primitive Pythagorean triples, then we can show that every primitive Pythagorean triple is of this form. But by just taking any m and n, we can always produce a Pythagorean triple. Now, for last part, I just want to show that for any values m and n, we will always produce a Pythagorean triple. Suppose we take any m and n such that they are positive and m is greater than n. And we let a be equal to m squared minus n squared, b is equal to 2mn, and c is equal to m squared plus n squared. So we shall see. Let us add a squared plus b squared. So this must be, this is m squared minus n squared squared plus 2mn squared. Yes, Alvin, can you, what is this?
That's m to the 4th minus 2 m squared n squared plus n squared.
Yes. M to the fourth minus 2 m squared
n squared
n squared plus
plus n squared.
N to the
N
4th.
fourth.
Okay. So if we perform the algebra, we get a squared plus b squared is equal to this thing. But we can combine negative 2m squared n squared with positive 4 m squared n squared. So we get m to the 4 plus 2 plus n to the 4. And we can factor this. This is nothing but m squared plus n squared is 2. But yes, m squared plus n squared is equal to c, so this is c squared. As you will see, if a, b, and c are given by these formulas, a squared plus b squared is exactly equal to c squared, which means that a, b, and c is a Pythagorean triple. It means that we can choose any m and n. So any choice of m and n would give us a Pythagorean triple. In my next lecture, I would show that any Pythagorean triple is actually of this form. Anyway, this is a wonderful piece of mathematics that was known to the Greeks. And the knowledge of these formulas enabled them to produce long tables of Pythagorean triples. Okay. For my last slide, I'll just show you some questions that you can take home to think about. First question, is there a Pythagorean triple, ABC, where A is equal to B? Second, is there a primitive Pythagorean triple, where the longest, where C is equal to 13? In fact, we found one, that's 5, 12, 13. Now, find a primitive Pythagorean triple with B equal to 14. Is that possible? And lastly, find all primitive Pythagorean triples with C equal to 17. Of course, I'm sure these are questions that you can now answer, because we had that formula that allowed the Greeks to produce tables of Pythagorean triples. So for my next lecture, I will go back to Pythagorean triples and give you a sense of the proof of that wonderful formula, and then I shall move on to some generalizations of the Pythagorean equation. So I hope you learned something, and I'll see you again at the next lecture. So for my next lecture, I will go back to Pythagorean triples again and show how we can come out with that wonderful solution, that wonderful method that allowed the Greeks to produce long tables of Pythagorean triples. So we should go back to Pythagorean triples, and lastly, I will give you a very nice generalization of the Pythagorean equation that has led to a lot of mathematics. So I hope you learned something today, and I'm also giving you something to take home, which is an assignment. So I'll see you all at the next lecture.
Thank you, sir.